Hello everyone. Today I'll present demo tutorial from human experience to multimodal software tutorials. The main problem is how to convert raw computer use experience into a reusable tutorial format. In many software tasks, human demonstrations contain useful procedure knowledge, but they are usually long, untrimmed, and hard to use directly. The paper proposes an agentic pipeline that converts screen video into interactive tutorial. In this seminar, I'll first motivate why tutorials differ from demonstrations, then go through the four components, and finally summarize the benchmark, experiments, conclusions, and limitations. To set the background, the authors position this problem inside instructional video understanding and computer use agents. Previous work has studied real-world instructional videos, procedure planning, and agents that act in GUI environments. But the paper argues that interactive digital environments are still underexplored as a source of procedure knowledge. In software usage, we often have two artifacts, a raw demonstration video, which is easy to capture, and a software manual or tutorial, which is easy to learn from. The problem is that these are not equivalent. A demonstration contains what the user actually did, but it is noisy and unstructured. A manual is structured, but authoring it requires significant human effort. Demo to tutorial targets this gap by automatically distilling raw screen recordings and instruction logs into structured tutorial. Here's the motivation of author. The paper makes a clear distinction between demonstrations and tutorials. A demonstration mainly shows what happened. It is a continuous, passive viewing experience. Often it has no narration, no visual highlight, and many redundant frames or irrelevant actions. By contrast, a tutorial is designed to teach how to do the task. It is step-by-step, more concise, and combines verbal guidance with visual annotations. This difference matters because the target learner is not just watching. They need to reproduce the task. So the core idea is knowledge compression and grounding. Turn raw action traces into actionable image text instructions. The paper also argues that this representation can benefit both human learners and GUI agents. The overall framework has four major components. First, the human experience recorder captures the input, screen video, low-level actions, and time steps. Second, the action parser uses those synchronized streams to reconstruct what the user observed, what action was taken, and what the likely intent was. Third, the step planner abstracts the flat action sequence into a hierarchical task graph. This means atomic actions become steps, steps become chapters, and chapters define the overall goal. Finally, the tutorial composer turns the refined task graph into an image text interleaved tutorial. It selects the most relevant keyframes and edits them with visual highlights. So the pipeline is recorder, parser, planner, and composer. Let me zoom in on the input side. The human experience recorder is important because a normal screen recorder only captures video. The others argue that video alone is not enough for reliable tutorial generation, especially when the user performs fast clicks or keyboard operations. HE recorder therefore captures three synchronized inputs. The first is full screen video, recorded as 30 fps using FFmpeg. The second is an action log, including mouse clicks, movements, drags, and keyboard inputs. The third is timing information. At the start of recording, users press a calibration hotkey while an on-screen timer is visible. This provides a shared temporal reference so that actions can be aligned to the correct video frame later. After recording, the action parser transforms raw logs and screenshots into semantic action captions. It has two parts. First, data calibration cleans the raw logs. It aligns the action stream with video frames using the hotkey time step, merges consecutive keystrokes within a 1-second window into a typing actions, and consolidates modifier key like Shift, Ctrl, and Alt into shortcut actions. Second, the VLM-based semantic parser uses GPT-4o with before and after screenshots. The interaction location is highlighted with a red bounding box, so the model is grounded on the relevant UI region. The output is structured into observation before, observation after, state difference, vector action, and inferred user intent. This creates the semantic trace used by the planner. The step planner converts the parsed action sequence into a tutorial structure. A key design choice is bottom-up abstraction, not top-down decomposition. It starts from atomic actions, groups consecutive actions that serve the same subgoal into a step, clusters related steps into chapters, and then synthesizes the overall tutorial goal. This helps filter out irrelevant operations while preserving the authentic workflow. For long demonstrations, the planner also chunks the sequence around a natural breakpoint, such as application switches or temporal gaps. The second key component is actor-created iterative refinement. The planner creates a structured tutorial draft, and the critic evaluates coverage, granularity, orderliness, and learnability. If the draft is weak, feedback is sent back to the planner for another iteration. The tutorial composer creates the final multimodal tutorial from the refined task graph. The first task is keyframe selection. Instead of sampling frames uniformly, it scores candidates from frames around each action using 4 criteria: text relevance based on OCR matching, image sharpness using Laplacian variance, motion stability to avoid mid-transition frames, and temporal proximity to the action time step. The best frame becomes the visual anchor for the step. Then the composer applies adaptive visual highlighting. Using segment anything to model for UI segmentation and rapid OCR for text regions, it adds click markers, drag traces, hotkey badges, magnifier effects, cropping, and highlights. The output is an interleaved image text tutorial in Markdown and JSON. Now I will discuss the evaluation of generation quality. The authors introduced Tutorial Bench, which contains 110 samples from 7 common software applications: PowerPoint, Word, Excel, Photoshop, Premiere Pro, After Effects, and Adobe Acrobat. Each sample consists of a task goal, a raw demonstration, and an official tutorial used as reference. The evaluation uses 2 score groups. The content score measures actionability, completeness, and conciseness. The visual score measures annotation quality and image relevance. GPT-4o is used as a VLM as judge, and the supplementary material validates this with a human consistency study. In Table 1, Demo 2 tutorial reaches an overall score of 86.2, outperforming human-authored official tutorials at 79.1 and all baseline methods. Its main advantage is the visual score, especially annotation quality. Beyond the intrinsic quality, the paper asks whether tutorials actually teach agents and humans. For GUI agents, they use Agent S3 on an OS Word subset with Chrome and VLC tasks. They compare the 4 context settings: prompt-only baseline, text-only tutorial, image-only tutorial, and full multimodal tutorial. Full tutorials performs best. For example, with GPT-5, Chrome success improves from 52.9 to 70.6, and VLC from 59.6 to 70.7. For humans, The others run a user study with 20 participants on a non-trivial PowerPoint animation tasks. Participants using generated tutorial finish in 131.6 seconds on average, compared with 174.1 seconds from demo video. Also, 16 out of 20 participants prefer the tutorial format. This supports the claim that tutorials are used for knowledge representation. To conclude, Demo tutorial contributes a complete pipeline for transforming raw human-computer use experience into structured multimodal tutorials. The framework is grounded in synchronized recording, VLM-based action parsing, hierarchical planning, and adaptive visual composition. It also introduces tutorial bench and tutorial-specific evaluation dimensions rather than relying on standard text metrics. The main empirical message is that structured tutorials can outperform raw demonstrations as a knowledge representation for both GI agents and human learners. However, there are still limitations. The current system relies on HE recorder action logs, so it cannot yet directly process arbitrary screen recordings without interaction traces. It also has efficiency and robustness issues. The supplementary material reports non-trivial runtime and cost, and failure cases including missing operations and mismatched visual text descriptions. Overall, the paper is a strong step toward scalable tutorial generation from human demonstrations.